Will do. All right. Well, welcome everyone to this afternoon's webinar. Today, we have great fortune to have Dr. Damian C. Brady to give us a presentation. Damian's professor in the UMaine School of Marine Sciences, professor of oceanography, and a member of the Aquaculture Research Institute at UMaine, based at the Darling Center. And his research focuses on how models can inform better decision-making in marine ecosystems to reflect values of coastal communities. Damian's research and his 24 or so team members, affectionately known as the Brady Bunch, focus on work on the intersection of oceanography and such things as aquaculture, offshore wind, marine carbon dioxide removal, the lobster fishery, and coastal water quality. And I'm looking forward to hearing his presentation today on storming and warming in the Gulf of Maine. So Damian, take it away.
Yeah, thank you, Chris. For those of you who were at the Aquaculture R&D Summit, R&D and E Summit, some of this may sound familiar to you, but I'm really excited to talk about the changes that are happening in the Gulf of Maine. And then I think, from the unique aspect of how is aquaculture connected to these changes in the Gulf of Maine. And if you've got questions along the way, feel free to put them in the chat and I can answer them, in the middle of the flow. I just maybe if Emily or Maya want to just interrupt me and say, yeah, there was a question in the chat. So feel free to do it either way, or we can answer questions or hopefully have a discussion at the end, because I think some of these changes are pretty nonlinear, and different industries in aquaculture are going to be affected in different ways. I started with storming because at least at the R&D and E Summit that we had in Castine, it was roughly around the year anniversary of the storms that really destroyed, by some estimations, I know MCFA, or the Maine Coastal Fishermen's Association, calculated something like 60% of Maine's working waterfront was in some ways impacted by the storming. So I want to talk about the storm and what the expectations are for storms in the future. And then I think similarly, we'll move on to warming, since it's sort of the dominant paradigm and how habitat is changing after the Gulf of Maine underwent this regime shift. Okay, so we got hit about a year ago at this time with a sou'easter that, as I said, destroyed, by some estimates, 60% of Maine's working waterfront. And so one of the deep questions I and a lot of people had, and especially in the Maine Climate Action Plan, for instance, is, what investments do we need to make in the future? Do we have to expect that these storms are going to happen more in the future? One thing I like about this slide, and these are provided by the Maine State climatologist, Sean Burkle, is it, sort of demonstrates why Maine is the tailpipe of the country, so to speak, right? So we have these long meandering weather systems that move across the North American continent. And this amplitude is driven largely by the difference in temperature south and north of us. And as that difference in temperature becomes less and less, this meandering actually gets longer. In fact, we've seen this with spring blooms in the Gulf of Maine, that these gray weather systems around this time of year, February, March, and April, linger a little bit longer. So if it's felt darker outside, that's because we've actually measured it. It's darker during this period of time, and it's actually affected spring blooms in the area. But you have these wide meandering systems, and some of them now meander a little bit west of where we're used to, generating the potential for these sou'easter storms. So that's where I'm going to start. Start with that. And this is connecting extremes via the jet stream late October and early November of 2019. This is just a snapshot. And when we get these kinds of storms, I think we're all pretty familiar with it generating dangerous storms here in California, and then creating dangerous storms on the East Coast on this side. Couple of examples of these, what sometimes the meteorologists will call bomb cyclones: October 2017, October 2019, and November 2019. During this period of time, we get these kinds of storms. And I should say that if we had the rain we've had the last 2 days, for instance, in 2 weeks on March 31st, when we see a king tide, we'll probably notice these kinds of events more and more. So let's talk about these sou'easters. These are similar tracks north into Quebec, producing strong southeast winds across Maine. For instance, on December 18th, before the January 10th and 13th storms of, so that's December 18th, 2023, then January 10th and 13th, 2024, we had gusts of over 70 miles per hour, 5 to 7 inches of rains in part of western Maine, and the worst flooding along the Kennebec and Androscoggin in almost 40 years. That's saying something. As a longtime resident of Hollowell, Maine, it's hard to imagine breaking records for flooding in that particular town. Storm outages similar to 2018, but I just want, or sorry, of 1998. But I just wanted to point out that this low pressure system, where these winds, because of the inland nature of the storm, were actually coming from the south, from the southeast. So, and then here's the map of the total precipitation. Developed against a strong backdrop of strong El Nino and record warmth across the North Atlantic. That's going to come in a lot of things that we discuss later. But one question I had for the Maine State climatologist, and I thought this is really, really interesting because a lot of people thought that a lot of the damage from the storm was because the wind came from a non-traditional direction. We're all used to nor'easters, but less used to sou'easters. And at least the preliminary analysis from the National Weather Service says that there's really no clear trend in the frequency of 1950. So there's not necessarily, because of climate change, now we're going to see an increased frequency of sou'easter events, at least, from the 50s to today. In each decade, the number of these kinds of events has not necessarily started to increase over time. So I think that's important for us to keep in mind, that the potential here is that this isn't necessarily something that's going to happen more frequently. However, I will say the intensity of these storms over time is certainly, there's a lot of evidence that demonstrates that is going up. And these are typically events that we would experience right around this time of year, or we just got through. What makes these events, even though they're happening at the same frequency as historically, more intense is, of course, sea level rise. So here's the annual mean sea level rise in Portland as part of the Maine Climate Action Plan on the Science and Technical Subcommittee. We had to update these maps, and 2023, we're at record sea level rise. This is courtesy of Hannah Baranis at the Gulf of Maine Research Institute, but sea level rise and water level ranks along the Maine coast. So the issue is that we can have the same storms, but under the conditions of sea level rise right now, we're going to generate a lot more flooding and, of course, a lot more destruction of our working waterfront, particularly those of us that are really, really interested in aquaculture. That's going to be a problem and something that we need to design for in the future. I thought this was really cool. This is an animation that Sean Burkle sent along that shows the nature of this sou'easter event, right? And I just want to highlight for you as this GIF recharges, sort of what happens. I'll do it one more time, but you can see it building up under warm North Atlantic water here, and then it becomes red when it hits Maine's coast right here. And that's just sort of the maximum amount of damage that this is gonna do for the Maine's coast. These aren't the first events like this. I think we're all used to some of these kinds of events are just starting to become more frequent, and with sea level rise, they are magnified. Okay. This is my quick aquaculture tie-in. For those of you that are running your own farms, you've probably sometimes heard from folks about resuspension. I think it's one of these aquaculture issues that stakeholders can get concerned about. As part of Acadia Sea Farm, for instance, and they've got a really cool setup here near Trenton. This is a quick aquaculture tie-in. They've been asked to describe how much resuspension from either dropping their cages on bottom to overwinter or raising those cages in the spring for summer grow out, how much resuspension maybe could impact this nearby eelgrass bed. So here's 2 tracks of their leases. Here is about 25 acres, I think, each of these. And here's an eelgrass bed that is right next door. And so you can sort of see that the high, mid, and low density on the eelgrass bed, for instance. And this is probably one of the more instrumented aquaculture farms in the state of Maine. We put current meters, we put sondes to measure the turbidity, we put temperature, salinity, and at all of these locations, and then allow the aquaculturists to put the cages down and then bring them back up and then measure exactly how much turbidity was caused by the overwintering of gears. What we did not expect is that we put all this instrumentation out during the January storms. And so I just wanted to show you why this is potentially impactful. But what you're seeing here, here's the January storm, January 8th. You'll notice that January 10th and 13th were the dates of those two storms from last time. I want to put here in perspective here, the turbidity at this site is 1, 2, maybe NTU units. That can roughly translate into 1 to 2 milligrams of suspended particulate matter in the water per liter of water. And, you could see through December all the way through January 10th and January 13th, where we get, explosive amounts of resuspended sediment from these storms. And here's the average wind speed, right? We went from three knots to 12 to 15 knots on both of these events, and that causes a tremendous amount of resuspension of sediment. And I only put this in perspective because we could hardly measure with the resuspension caused by overwintering the cages, by raising and lowering the cages, because we were getting so much suspension just from the storms. So if these eelgrass beds could traditionally handle some of these storms, we feel like they're probably okay in just moving cages up and down. So, and just to put that in perspective, here's what happened. It went from 0 to almost 50 in the first storm and 0 to 150 NTU units. When I come down here to when we were actually raising the cages, we're talking about 1 or 2 units of NTU increase when the cages were being raised, and that's right on farm. We couldn't measure any changes in turbidity on the eelgrass bed, for instance, right? And maybe a little bit on the midpoint. So you can see some resuspension here. This red line is the midpoint. It's a son that we had in between the eelgrass bed and that area. And then this blue line is the eelgrass bed. So really, really cool, necessary data, I think, to start demonstrating that some of these overwintering activities are probably not having a big effect 100 or 200 meters away. All right, so let's leave storming for a little bit and talk about warming. The way people talk about warming is, I think, really important because it's just important. I think it's important to understand what happened to us, right? This is from the Gulf of Maine Research Institute. They do a great job of updating this every year and showing you the annual warming trends through 2023. And I just want to point out that the global ocean average, they say here, is about 0.29 degrees of Fahrenheit per decade. And here is the Gulf of Maine sitting at, roughly 3 times that at 0.87 degrees Fahrenheit per decade. And so this is the blue line here is the trend fit to these dots, the annual sea surface temperature anomalies for the Gulf of Maine. I just want to point out, though, that if you actually really squint and look at this graph, what you're going to notice is that from 1980 to roughly 2008 or 2010, the temperature went up, the temperature went down. There's NAO, the North Atlantic Oscillation. So there were sort of regular patterns of how what was happening in the Gulf of Maine. And so then you should notice that at some point around 2010, we move into what we think of now as just simply a different regime. So this is just now the temperature is going up and down the way it used to back here, but you can see it's elevated, and roughly about 2 degrees Fahrenheit is the level of elevation. So I say that because everyone says, hey, the Gulf of Maine's warming faster than blah, 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 blah. But what in point of fact has happened is that it warmed over a short period of time into a new normal. And here we're in a new normal. That's about 2 degrees or 1.9 degrees Fahrenheit higher than it used to be. And I say that right because if we thought, if I connected a line from 2002 to 2012 right here, and I connected that line, and then I said, hey, look at this warming, you would, if it was continuing to warm at the pace of 2002 to 2012, the water would be boiling right now, right? So this rate of warming, as Andy Pershing correctly pointed out, was faster than 99% of the world's ocean. But I really think it's important now that we have a little bit of a perspective. If I connected this dot with 2023, we'd say, okay, there's very minor warming happening since 2010. And in point of fact, 2024, we're going to have the year we just experienced was the seventh warmest year on record in the 20 or so years that we've been tracking this, right? And that doesn't necessarily mean that the Gulf of Maine isn't warming. It's just we're in the new normal where every year is going to be in the top 10 of warming years. For those of us that are aquaculturists, I think we're oftentimes wondering about the summer sea surface temperature. So these are the warming records of the summer summer SST. And I just want to point out that the warming trend in the Gulf of Maine for the summer is even worse, right? So the summer period is the period that's warming the most. For those of us who raise oysters, this may actually be good news, right? For those of us raising kelp, maybe not so great news, depending on the length of the season. This is kind of cool. It's an output that they have there, but what it tries to do is it tracks marine heat waves. And they define marine heat waves as X number of days above the 90th percentile for what we expect in these habitats. So in 2024, we roughly had 32 days of what we would call a marine heat wave for about the month of June last year. So if you saw that at your site, that's the kind of situation that we were dealing with. And again, for some organisms, that's probably a really good thing, moving into the hottest part of the year for, let's say, the oyster industry. Okay, so I just wanted to make sure that we sort of put in perspective that what happened to us is a regime shift. It's not like the Gulf of Maine is sitting under the sun, getting warmed every year, just getting a little bit warmer and a little bit warmer, but rather the mix of water that came into the Gulf of Maine changed rapidly at around 2010. So let's try to get a sense of like how that looks, what I mean by that, what the Gulf of Maine really looks like. This is an incredible sea surface satellite picture of temperature in the Gulf of Maine and elsewhere. And I'm just pointing out this green plume of water because we're going to look at this green plume of water that comes down here along the Scotian Shelf, ends up here in the Bay of Fundy, coming down to down East Maine. And in point of fact, I like to tell people there really are two Maines, right? There's the eastern Maine coastal current, which is well mixed and always cold. It's this green water coming down the Labrador Shelf, the Scotian Shelf and Labrador slope water coming in here. And then you have the western Gulf of Maine, where a lot of us as aquaculturists operate. And that western Gulf of Maine is oftentimes hotter. You can see that right here. It's going to become stratified because this water is slowly getting warmed as it makes its way down the coast, up the Bay of Fundy and down East Maine. So there are these two really, really important current systems we're going to talk about. One is called the Labrador current system. That's this blue line right here. And the other is the Gulf Stream, warm slope water from the Gulf Stream. So it's warm, salty, it has high nutrients, and then cold, less saline, low nutrients with respect in particular to nitrate. So these offshore sources of slope water, I like to think of the Gulf of Maine as a kiddie pool, right? And it has two hoses that go into it. There's a cold hose and a warm hose. And it's actually then really, really easy to warm the Gulf of Maine fast by pinching off the cold hose and leaving the warm hose on, which is what we think happened around 2008, 9, 10. And so this is our previous conception of how the Gulf of Maine works. We have a West Greenland current. It comes around Greenland. Greenland is discharging fresh water all the time, enhancing these coastal currents, coming down here along Labrador, where it becomes what we call the Labrador current. And the Labrador current has some offshoots. It goes in near to north to Newfoundland. We can follow the Labrador current all the way down to a really important place for our conversation today called the tail of the Grand Banks. And here is the Grand Bank off the coast of Newfoundland. That cold water that's coming down the slope here would normally take a hard left, come over here, become Labrador slope water, and that Labrador slope water would come in over the Scotian Shelf or through the Northeast Channel and then enter into the Gulf of Maine. And this is typically what we thought is happening for the most part up until around 2010. These waters also meet with the Gulf Stream North Wall. This is the strength of the Gulf Stream during this period of time. And then they meet in what we call the slope sea. So there's some mixing Labrador slope water and warm slope water in the slope sea. Last thing I want to say, because I think it's been less advertised and less thought about, there is a third current here, which is called the Scotian Current or Nova Scotian Current or Scotian Shelf water. And that water actually has a much more direct access into the Gulf of Maine. That becomes really, really important in the winter. And we'll notice that there's been a sharp cooling in the Gulf of Maine in parts of last year, probably caused by the Scotian Shelf water. So the slope C, an area of mixing. So we've established that. So sea surface temperatures north in the Gulf of Maine and then south. We are, and by some estimations, the Gulf of Maine is sitting at the sharpest gradient in temperatures in the world latitudinally, which is why in every model that gets run, the Gulf of Maine is one of these places that we expect to be warming into the future very rapidly because we sit at this gradient. So just small shifts in the gradient north and south mean big changes for us, which is what happened to us in 2010. Okay. So these slope waters and their mixtures spill into the Gulf at depth through the Northeast Channel and along the shallow Nova Scotian shelf waters that enter around the Gulf of Maine. So there's the Northeast Channel, and here's the blue Scotian shelf water. This has been known for a long, long time. In fact, this is data and pictures from Henry Bigelow, H.B. Bigelow, who was the first oceanographer to really characterize how the Gulf of Maine worked. Deep and bottom slope waters, salinities over 34 PSU or PPT, depending on how you define it. And these waters would come in basically in these two directions into the deep holes of the Gulf of Maine, and there's this shallow Scotian shelf water that comes up over the top of that. It's really cool. The images now you can see, this is an SST picture from 2022 in Rutgers, but you can actually see this super blue cold water coming in around this area. All right, so then something changed between 2008 and 2009. So let's see how we can characterize what changed. And this paper really helped a lot of people understand what happened. Changes in the Gulf Stream preceded the rapid warming of the Northwest Atlantic Shelf. There's actually been some really interesting papers since then, but I just want to give everyone a sense of what kind of data helped us understand that. There's something called satellite altimetry, and in situ measurements show that in 2008, the Gulf Stream migrated closer to the tail of the Grand Banks, and a shift that has persisted ever since. Satellite altimetry is a really, really cool technique where the satellites can tell us sea surface height. So they can tell us very accurately now how close or rather the height of the ocean at relative time. So if one part of the ocean is a little bit higher than the other part of the ocean, you can almost assuredly think that that flow has to move from where it is higher to where it's lower. So these satellites now in real time can give us how high the water is. And what's really cool is that what they showed was that the sea surface height at the tail of the Grand Banks was higher in this area where my cursor is, so that hopefully you can see, but near the tip of the Grand Banks. And that water flow or that height of the water began to pinch off this Labrador slope water that we rely on in Maine to be colder than the rest of the East Coast, right? I mean, our waters are much, much colder than everything south of Cape Cod. So this is what we think the after 2000 to 2008 scenario looks like. Instead of this Gulf Stream meandering, this Gulf Stream is a little bit more north, a little bit more straight. Our slope C is smaller, but more importantly, the Labrador shelf current can be entrained in the Gulf Stream water, and more of that water is starting to move east. Less of that water is making its way west and into the Gulf of Maine. And this is sort of why, at least right now, we think that this big flip changed. And now I want to talk a little bit more about how this large-scale oceanography affects us as aquaculturists that working in these local estuaries that are adjacent to what just happened to us.
Hey, Damian, I have a quick question about that previous slide.
Yeah.
I'm wondering if it's like what the predictions are for like how far north the Gulf Stream could move and whether it would potentially pinch off the Labrador current around Newfoundland as it's coming down into the Scotian Shelf and the Labrador slope water.
Yeah, that's a super good question, Maya. But one of the things that protects, I think, this sort of north of the tail of the Grand Banks is that the Gulf Stream is moving along a bathymetric feature here. So there's really a limit to how far it's going to sort of come up and pinch water off. And in fact, you know, this drawing here conceptually is something that may be useful to think about how the water's moving, but it's probably not accurate. Because, in 2024 was the 7th warmest year on record. So more Labrador slope water we think came over. Actually, we think there's more Scotian shelf water over that period of time. So there are going to be periods where it meanders and allows Labrador slope water to come back. But I think there's a limit to where the Gulf Stream is going to move north. And that's why this tail of the Grand Banks becomes really important, because now I can look at satellite altimetry right here and say, is it conditions where this, again, bathymetric feature, this geology that's controlling the flow, is this is just a pain point right now. And that it can do more damage just because there's a little bit of bathymetry that squeezes up against the current systems, if that makes sense. So we think that what's happening is that there's less Labrador slope water delivered to the offing of the Northeast Channel, and we also think that we have a smaller slope sea. I won't get into it now. This is just another one of these images that I think are super cool that we somehow can generate now. It shows the Eastern Maine coastal current and how cold it is, but it also shows that there are now these massive eddies and warm core rings. So a lot of us have heard about warm core rings, and we can see this in our Nearcoos record of all the buoys that are out here, that there's actually water that sometimes is very salty, very warm, that sweeps through the Gulf of Maine. And so there is a lot of research, really interesting research, that in addition to the potential of the Labrador slope water to get pinched off to the Gulf of Maine, that there's potentially more of these warm core eddies that are actually entering over the top of the Gulf of Maine and coming into the Gulf. Okay, so what does this mean for the future? There's a really cool paper that came out pretty interestingly, a predicted pause in the rapid warming in the Northwest Atlantic Shelf in the coming decade. So they take a really, really high resolution model and they say, okay, I can do a good job of capturing what's happened in the Gulf of Maine over time. I captured the 2010 event. So this is the black line is the data and the dashed line is this model. And so now I'm going to use the models to sort of figure out what the next 10 years is going to look like. And maybe unsurprisingly, once you have this regime shift change, it appears like that we are going to be locked in this regime shift. So this warm water that we're seeing right now, most of the models are demonstrating that we should sort of continue to be bouncing around this new normal. At least right now, the models don't predict that we're going to see a 1 to 2 degree Fahrenheit change over the next 10 years. So their conclusion was that we should expect a temporary respite from rapid Northwest Atlantic warming is forecast for the coming decade. The forecast warming pause is attributed to just a modest strengthening of the Atlantic meridional overturning circulation, which is a fancy way of saying that this Gulf Stream pinching we don't think of as going to create a much stronger pinching off of Labrador slope water, at least over the next 10 years. I probably have this number wrong, Emily. I just had it in the slide before, but one of the cool things that Emily Whitmore was finding in her survey of growers and aquaculturists, and I'm curious how this group feels about it, is that a lot of growers want to share their data. I think we find the same with American lobster fishermen. This is a lobster fisherman, Charles Bennett, who reached out to me. And he is clearly looking at the Nearcoos buoys, at some rate, which I think is really cool because I think we should all think of ourselves as scientists. And he sent me this email saying, hey, I was wondering if you have any idea why the salinity and water density are so low. And he's in Down East Maine. I look at the Eastern Maine shelf buoy, but scrolling through the others, they all seem very similar. This was, March of 2024. And I thought, okay, what is he talking about? And I went and I looked myself and yeah, sure enough, here's the salinity. Usually the salinity of the Eastern Maine shelf current is 33. And all of a sudden now it's below 32. And I actually didn't know the answer to this question. I spoke a lot to Dave Townsend and other oceanographers here. And and one of the cool things that we found out is that there is all this Scotian shelf water, which is a little bit more fresh. It's coming along the Scotian shelf. That Scotian shelf water is entraining all the little rivers from the Gulf of St. Lawrence all the way around. And so that nearshore water from the Scotian shelf water tends to be colder and fresher. And lo and behold, he was essentially detecting this plug of Scotian shelf water that was coming into the Gulf of Maine. And a lot of people are detecting that with the seventh, warmest year on record, and not the first warming year on record, that the Gulf of Maine was actually a little bit chillier last year than we would have expected. And some of it is the Scotian shelf water. So this just gives us an idea that from 1998 to 2010, there was a roughly equal mix of this Labrador shelf water and this warm shelf water. And then it really took off in 2010. But lately, anyway, with the introduction of more Scotian shelf water, we seem to be coming back to a sort of a different or new normal. So if you feel like the Gulf of Maine is cooling just ever so slightly, it may be that there's a little bit more Labrador slope water that's making its way in and a little less of this warm slope water. I'll be super curious what this year looks like, whether this is a very temporary pause, but the data and the models seem to indicate that we are just going to be in this new normal of this new regime shift.
Hey, Damian, sorry to interrupt again. I just wasn't quite clear on why there's more Labrador slope water coming in into the Gulf as opposed to the warm slope water.
Yeah, so this is from NOAA's. NOAA has an state of the ecosystem report that they put out, and they define water based on the temperature and the salinity of that water when it comes in. And actually, it's really, really hard to distinguish Labrador slope water from Scotian shelf water. So where it says LSW here, that means Labrador shelf water and Scotian shelf water, because they just don't know how to tell the difference. So this is the thing that I'm noticing that people are sending me now is that there's just more Scotian shelf water coming into the Gulf of Maine. So we seem to be, we still have a lot of warm slope water. By the standards of most of our monitoring, there should be like 50% warm slope water in the Gulf of Maine, and now there's 60 and sometimes 70% of the water inside the Gulf of Maine is warm slope water. But it seems to be maybe coming down, and we think that that's less about more Labrador slope water and actually more about more Scotian shelf water. So it's still lots to learn on that, but if that's sort of the sense right now, is that you reach 2012 heat waves, and 2021 was, again, one of those super duper hot years, but at least the last couple of years have been sort of this new normal. Still very warm, but 60% of the Gulf of Maine is this warm slope water instead of 70. And we think what's making up the difference is the Scotian shelf water that's coming in.
Okay, and could that be coming in kind of as a result of glacial melting?
It's possible the strength is there. We have a smaller slope C overall. And so the influence of the slope C may be like lowering in general, which is allowing water that just simply comes over the shelf to come in and enter. One of the things that was sort of disappointing, and the Congress passed the new continuing resolution, which we're probably maybe all aware of, but in the original budget, we actually had a project to put a lot of buoys at the Northeast Channel and actually give ourselves an early warning system for these kinds of changes. So we're still pushing toward that because it's really hard to pick out what's the Scotian shelf water and what's Labrador slope water.
Thank you.
Yeah. We do think that a lot of the production in the Gulf of Maine is linked to how much Labrador slope water we have. So a drop in chlorophyll after 2010 is not the result of less Labrador slope water, but the result of a drop in total slope water, which resulted in a lower nutrient flux and lower salinities. So that's something that we've been tracking too, is that the overall chlorophyll, if we look at satellites, has dropped in the Gulf of Maine as a result, and now is rebounding as we get more of this Labrador slope water and Scotian shelf water in the Gulf of Maine. So things are changing, and this little way of looking at the world is actually pretty useful, because you can see the amount of Labrador slope water that's in the Gulf of Maine is usually pretty good at helping us understand the amount of chlorophylls in the Gulf of Maine. All right, so why do we care as aquaculturists about these huge changes that are happening in the Gulf of Maine, but I have my farm up in Casco Bay or Damerscott or Penobscot? This is kind of a cool map that just shows that the Gulf of Maine estuaries have deeper openings to the ocean than anywhere else on the East Coast. So what happens in the Gulf of Maine doesn't stay in the Gulf of Maine. What happens in the Gulf of Maine affects all of our estuaries because the mouths of our estuaries are 100 meters deep, very close to shore. If I'm doing this work on Long Island Sound, you can see that it's about 50 meters deep right up to there, and 100 meters deep is offshore. So Maine is unique insofar as that all our estuaries have deeper openings to the ocean and are therefore more affected by what happens in the Gulf of Maine than anywhere else on the East Coast. Most of the time, this is a good thing. We love this. Sometimes not such a good thing. Also, because Maine is a deglaciated watershed landscape, where we used to have 5 kilometers of ice above my head right now, 15,000 years ago here. It means that the Gulf of Maine is fed by hundreds and hundreds of small estuaries, and we and the community of growers are out there essentially have every grower that is in one of these estuaries, and I've just delineated the watersheds here in the hydrological units, just to demonstrate that we have hundreds of different little areas where aquaculture might thrive differently in any of these areas, right? So I've got my salmon areas out here, I've got my seaweed areas and my strong shellfish areas in this mid-coast, and everyone is essentially growing their product in an adjacent landscape that's totally different. And that reason that that's important is that river influence is relatively small in Maine, and the ocean influence is relatively big. So that's why I say, it's always a good idea to pay attention to what's happening in the Gulf of Maine. All this Gulf of Maine stuff is great, but it's not where I live. This is a super cool figure, I think anyway, that Tom Kiffney put together, that he just maps all the LPAs and all the standard leases in the Gulf of Maine and how far they are from shore. And just, notice that most people are within a kilometer of shore in the Gulf of Maine. That's going to come up importantly in the future here, but everyone's pretty close to shore. So the only way that we can then monitor those areas, because we can't put 543 Nearacus buoys in all of these estuaries because they're all, because that would be extremely expensive. We need new tools that help us understand these nearshore areas where aquaculturists are operating. So I'm going to show a couple of pictures of these high-resolution satellite images that we've been taking along the transects of all these long, straight estuaries that were all glacially carved here in the mid-coast. But, when we can do anything I'm saying right now in a lot of these other estuaries too. So here's the Damariscotta. I've taken it, I've picked it out of the map, I put it on its side, and then I want to map using high-resolution satellites what's happening all along the transect of the Damariscotta River estuary, just using satellites and remotely sensed. So this is just the temperature. So I can take this transect up the Damariscotta, and I can plot the temperature, the average temperature here in the Damariscotta, which I think is totally cool. I mean, when I first started doing this, I never thought that this would be remotely possible, but now it is. I've highlighted where 20 degrees C is or greater, and that's just, to highlight maybe potentially what's a good oyster growing area. You can see that what the Damariscotta River is doing is it's heating seawater. It's taking seawater, it has almost no river, it takes that water and then it heats it 5 degrees Celsius. The whole point of the Paris Climate Accords is to reduce 2 degrees centigrade changes globally as a result of climate change. By itself, the Damariscotta is heating water, and if you're in Great Salt Bay, 6 or 7 degrees centigrade. This is the magic right now of this particular habitat, right? Damariscotta is sitting there heating up seawater, and now we can see this from space, and we can give you a picture of the Damariscotta every 5 to 16 days of what's happening along the axis of the estuary. But even cooler, and I should say that this sharp increase in temperature that you're seeing here, that's Glidden Ledges. So that's an actual geological feature that's holding on to water. And you can see that the upper part of the estuary is on a whole other trajectory. We can see this in everything that the Damariscotta is doing to provide for aquaculturists, and I'll show some other systems too. This is this point called Glidden Ledges again. What I'm plotting for you is the particular organic matter. You can roughly think of this as oyster food. Chlorophyll, another indicator of oyster food. I take this transect all along the Damariscotta River estuary, and then lo and behold, I can see that the upper Damariscotta is doubling my food. It's retaining food, particulate organic matter. for bivalves. And basically that little feature there, Glidden Ledges, is doubling the amount of food and then sort of changing the amount of chlorophyll that's up there. It's also very variable, so it's not always going to be like that. But it's really, really cool that now I can use this and look at any estuary, for instance, and see what's happening. So let's take a look at another one. Here's the Madomic. Most clammers in the state has a really, really vibrant and strong clamming community. We can look at the kinds of things like the constriction here, for instance, is another great area. So this is up near Waldoboro. You have this huge clam flat area up here in northern Madomic. Then you have this constriction here of islands right here. And we can tell, similarly, there's more actually particulate organic matter in the Madomic than there is in the Demerscata. You're talking 2 milligrams per liter. And if I showed you before, like we're at 1.5 in the Demerscata. This is a very food-rich environment that we're talking about here. Similarly, we can see the kinds of constrictions that cause temperature changes up here. It's not nearly as good an estuary for warming seawater up, but it does retain a lot of food. Here's the New Meadows. I know some of us operate in the New Meadows, which is a super cool system, but you can tell why growers are targeting the northern end of the New Meadows, right? So some of the it actually remains pretty cold. I mean, it's a southern estuary, so it's a little bit hotter than these other places I showed, but it doesn't do nearly as good a job holding onto water and heating it up until, you get to the really, really northern end of the estuary. And then it does a really good job of spiking the water and holding on to organic matter, which is, pretty cool to see. And again, this is all from satellites. Sheepscot's a much tougher system to operate in. I found I'm flabbergasted that it's basically cold already, 15 degrees C instead of 18, and then it doesn't do any heating of the water at all, right? So this is a fantastic estuary if you want to raise a cold water species, and you don't want a lot of dynamism in the particulate organic matter, which is about 1/3 of the Madomic, for instance. Chlorophyll relatively low and unchanging. So this is just an estuary with a super deep draft. I put the bathymetry up here. It gets 60 meters as the water comes in. It's taking really cold Gulf of Maine water. It's not really holding on to the water all that well, and we can see it all via satellite. What's really cool is Tom has taken this to this whole other level, and he's actually using the satellites to track temperature over time. The Landsat satellites have been up since 1985. This dark line here is from the Boothbay temperature record that DMR has been keeping. The satellites and Boothbay's record, DMR's record, are largely in sync. And now, what this really means is that we could actually track temperature time series for any one site that's really, really interested in how potentially it's been changing over time. Here's an example. We took 3 sites in the Demerscata. We did the same thing from 1985 to the present, and we looked at changes over time. And it's funny because I need to go back through this, right? But there was a similarly interesting, strong warming period from 1995 to 2000, a sort of cooling off, and then in 2010. By most of the Gulf of Maine is warming. We can see that what was happening in the broader Gulf of Maine at the beginning of the talk has been happening to all the sub-estuaries, particularly estuaries that are not river dependent. And so the Demerscata clearly a non-river dependent. It is warming as a result of those things. I should say it's warming a little bit faster in the upper part of the river, and that may be because you get atmospheric warming that's warming the water, and then you also have Gulf of Maine warming that's warming the water. This is a cool plot that Tom Kiffney put together, but it's just asking how many days are above 15 degrees C. Those of us who raise oysters realize 15 degrees C is a pretty good indicator of how good some of these habitats are. And I bring this up because it's kind of cool to see that there's just generally the season has been lengthening. So if you're in the mid-river near where I am sitting right now at the Darling Marine Center, you went from 90 days to 120 days. So there's a month of extra grow time that you get now. And you can see the farms popping up just outside my window as a result of the fact that you have this extra month of growing. Similarly, though, you're not getting, because the number of days over 15 degrees C in the upper part of the river where a lot of farms are, you're going from 120 to probably 140. So you're probably maybe 20 days of extra time. But it's interesting that some of the lower river now is, where we're in closer to Booth Bay. Now, all of a sudden, you're talking about 90 days of above 15 degrees C. So what is the future of this industry that's looking and mining for periods of time that are, above 15 degrees C? I won't go into too deep work on this, but Tom has used a lot of this satellite imagery to actually start plotting how fast an oyster would grow in these situations. If you're interested in this, please let me know. But one thing that we found is interesting is that the actual amount of food in the, tracked by satellite over time, and some other ways that we have of tracking it has actually gone down a little bit in the Damascata, even while the temperature has gone up. And so we have to balance those two things. If we're going to have issues with food quality or food quantity in these areas that are warming, we have to balance it against the fact that there's all these positives from higher temperatures for certain species. So the Gulf of Maine sits at a really complicated interface between the Gulf Stream and the Arctic, and it makes it really difficult to predict what's happening in the future. At least the current models think that the next 10 years will stay in this in-between area. Our warming is most often caused by changes in the water masses that enter rather than the direct heating from the sun, for instance, or the retention of heat. The great majority of our aquaculture is happening near shore, and we have new, very cool tools like satellites to track warming, nutrients, and food. Please reach out more about that. I'm very, very excited about trying to launch a program that similar to the lobster fishery. The lobster fishery has something called EMOLT, electronic monitoring of lobster traps, where we put relatively inexpensive temperature sensors on lobster traps. They haul the trap, the temperature gets recorded on a deck box, and then can go into a larger database. What's really cool about these new sensors is that they have an accelerometer in them. So as soon as the trap feels like it's about to get hauled because it's shaking, it increases its sampling frequency and also gives us profiles. And because we all operate in areas with variable connections to the Gulf of Maine, coordination and data sharing would be very, very cool. Okay, I think I'm done, Maya, so.
Awesome, Damian. Thanks so much. That was a really fantastic webinar. I'm going to add another spotlight here. So we can take questions from the audience. We don't have any in the Q&A yet. So while the audience is thinking of questions, Maya has a question. So take it away, Maya.
Shockingly, I have another question. So I know you were just talking a lot about the estuaries and kind of the temperature and chlorophyll dynamics there, which is really fascinating. And I was wondering if some of those are like they're kind of being affected a lot by some of the changes. I'm wondering about like a little bit further offshore, if like looking to offshore options for aquaculture is a good strategy to potentially reduce impacts in like extreme variability, since a lot of times the variability is the bigger issue than the actual like temperature itself.
Yeah, I mean, if I'll boil it down, so the amplitude of seasonal variability in temperature and food is really, really high and you're near shore. And then if you go offshore, you have a much more stable temperature profile. And I think, one, it'll depend on the species. And then two, of course, it depends on the husbandry practice, right? Because the moment you go offshore, everything, your ability to operate gets so expensive, right? I think with scallop and scallop aquaculture, where we spent a lot of time, and we wanted to be between 12 and 15 degrees C for as long as is like possible. And offshore areas are really, really good at keeping water between 12 and 15 degrees C. And then the question will be, can you have your farm, and mussels, I think, are in the exact same boat, right? So then the question is, can you have a farm that's somewhat protected, and not exposed all the time? Or can you protect your farm by using semi-submersible floats? And so this balance between finding the environmental conditions that are optimal for the species and something that's economically feasible to do is the real challenge. But for mussels and scallops that want a very stable and relatively low temperature, there's our models are showing there's plenty of opportunity out there for those farms if you can find the right place that's feasible to work in.
Awesome. Thanks, Damian. We have a few questions. So given these data sets, can we start to look at shellfish carrying capacity for some of the larger growing areas?
Yeah, we can. It's a complicated question because um, yeah, for lots of different reasons. But one of the complicating questions is that shellfish actually change nutrient cycling, for instance. And so a lot of folks on the Damascata feel like, one of the interesting things that shellfish do is they turn dissolved inorganic nitrogen, so the base of the food web, into particulate organic nitrogen, which is something that can sink and can stay in an area. So you can pump this area with nitrate, a dissolved inorganic nitrogen, and oysters can eat it and turn it into feces and pseudofeces and keep it in that environment and then let it cycle and actually create more food over the long run. So that can happen. But every time you harvest an oyster, you take nitrogen out of the ecosystem. And then I think the deep question that many people are asking, is it possible to have oysters so densely seeded in your farm that they actually remove organic matter that other adjacent ecosystems can use? We don't see evidence of that in our chlorophyll sampling, right? So we don't say like, oh gosh, like over the course of 20 something years of monitoring chlorophyll in the upper Damascata, for instance, where there are, we think right now, probably 20 million oysters, we don't see like, oh, we ran out of organic matter, right? There's always about 5 micrograms per liter of chlorophyll, but there's always obviously a limit, I'm sure. It's just that even at the number of farms in the Damascata, which is probably the most densely farmed area in the state, we're not seeing like, oh, well, there's the chlorophyll used to be 5 micrograms per liter, and now it's 2 micrograms per liter. And if you're an adjacent clamming bed, for instance, like that, you're not getting enough organic matter. At least we haven't seen evidence that we're at those kinds of densities at 20 million oysters. But it's pretty easy to calculate the volume of the Damascata, the 20 million oysters, take their feeding rate, and say like, well, every day, there's twice a day, actually, the tide delivers new organic matter and nutrients and turns it into food. It's pretty easy to sort of say 20 million oysters can only eat this much chlorophyll, and there's just too much chlorophyll being delivered at each tide.
Great. Next question. What is the resolution or pixel size of the satellite imagery that you're using to map temps in these estuaries?
Cool. That's a really cool question. And it's, part of the reason that I had this slide that Tom put together that shows all of these areas that are within 1 kilometer. Just, stress everyone operating in the state of Maine is within 1 kilometer of land, with, for obvious reasons, I guess. But the resolution of a lot of the satellite imagery that I showed, that I think are cool, like this is Modus Aqua. This is an ocean satellite that has a 1 kilometer resolution. So none of the farms in the Gulf of Maine could be seen by this satellite accurately, because they would basically pick up land. Land is very, very bright. It has a high reflectance, so you can't get any information and data if your satellite is reflected off of land. And so the new satellites that I'm referring to, Landsat 8, 9, Sentinel-2, A, B, all the litany of like crazy satellite names, you can have a 30 to 100 meter resolution depending on which satellite you're looking at. So at 30 meters, now I can be 90 meters, a couple hundred feet from shore, and actually get really interesting and good data. I mean, 30 meters, now we're at the scale of a farm. You can tell me where your farm is, give me a lat and long, and we can plot like what the environmental conditions are, which again, first time really that we've had this capability is about 2017. So I think for most growers and for most researchers, we're still trying to figure out how the cool things that we can do with these new satellite products.
Great. One more question. My farm is in Robin Hood Cove, which is just off Sheepscot. This is not my farm, the audience member's farm. Just off Sheepscot. It's very shallow, very warm, big temperature difference with the Sheepscot. Wondering if that temperature difference on tide mixture helps with nutrients.
Temperature is inversely correlated with nutrients. So the colder your site is, that's very likely to have more nitrate and nutrients, right? So, and that's because this the temperature of your water is essentially a proxy for when it last saw the sun. I like to say that it's a place for time. So that if your temperature of your water is cold, that means that it may not have been mixed into the surface in quite some time, and therefore has been cut off from surface heat radiation. And therefore, phytoplankton haven't had a chance to use it. So that water is rich in nutrients because of the fact that it hasn't seen the light in a while. So, and I should say, like when I spoke about the Sheepscot and Robin Hood Cove, very cool area, what Tom and others are discovering is that while I take a transect in the middle of the estuary, it's not great oyster grounds, right? But if you take the full satellite imagery and look at all these coves off there, the individual coves have enough residence time to increase the temperature just a little bit to be a pretty interesting place. So when we map now on our satellite images, all of the sites in the Sheepscot, everyone is sort of using the edges of the Sheepscot to try to find these areas like Robin Hood Cove, right, that are doing a little bit of residence time for me, while also maybe taking advantage of the fact that the Sheepscot artificially is like an upwelling area. You have really, really deep draft. You have 60-meter water that's coming into the estuary that's probably rich in nutrients.
Fantastic. Looks like we got through all the questions from the audience members. We might have time for one more. And if another one doesn't come in, I'm just curious about, you've talked a little bit about projects on the horizon. Do you have any others that you haven't shared of future projects you're excited about?
Yeah, I'd say the big one that we're excited about would be, something we're trying to call like EMOA, electronic monitoring of aquaculture. So I would love that, if people are really interested, getting some of these low cost sensors on your farm, and putting a deck box on your boat, and every time you flip your gear, for instance, it comes out of the water, for instance, and then uploads that data. We could even get you air temperature, depending on how much you want to share that information. I think rightly, most aquaculturists I meet think of themselves as stewards of the environment. They want to be out on the environment. It's in their best interest if the environmental quality is high. And if we could get a network of growers along the coast, we would be doing the thing that is almost impossible to do, which is monitor nearshore estuaries in the state of Maine, where you have 3,600 miles of tidal shoreline. It's impossible to monitor this without strong coordination, or some kind of distributed sensor network. And I think of every aquaculturist as a potential node in a really, really cool sampling platform that we could put together.
Awesome. All right. Well, thank you all for coming. Fantastic webinar. Thank you, Damian. Our next webinar will be April 18th. So keep an eye out for flyers about that. And also a recording of this will be available. So you'll probably receive that since you've registered, but feel free to share the recording once it's out there. And thank you very much, everyone.
Thank you. Appreciate it.
Thanks, Damian.
Thank you, Damian.